Hello and welcome to this special edition of the Klingberg Wing Mark II development. We're going to do something a little different today. Um, and I'm posting this for everybody to see, for the general public, because I'm going to ask you for some help. And I know one of you out there has the information that I need, and I hope that I can reach you this way. Um, Today I'm going to talk about a terrible accident that occurred back in the early 90s with the Flair 30 hang glider shown in the picture here. The Flair 30 was being developed over in Europe about the same time that I was developing my first wing, about the same time that the Swift was being developed. The three aircraft are relatively equivalent to each other. They're all composite and they're meant for high performance hang gliding. Um, my first wing, as you know, came to an inglorious end when it spun in at Torrey Pines, and much of my work since then has been devoted to preventing spins on flying wing aircraft. The Swift has proved out to be a very successful glider, and it's not totally spin resistant, but it is proven itself over time to be a perfectly safe aircraft. The Flair 30 suffered a fatal accident well into its testing and flying. And it has always perplexed me about what actually happened in that accident because there were probably a number of people watching that have the at least modicum of technical expertise that's needed to explain what went wrong. Um, Unfortunately, the test pilot died in the accident, so there was no information to be gained there. Um, and it is always reported that, in fact, the part that I'm reading here from, actually, this is from Nest of Dragons. This wonderful website has all the hang glider and rigid wing information on it. Uh, I've been reading on that website, and I'll read some of it to you here in a moment. Um, and the way they explain the accident and what happened as an aero engineer just really didn't make sense to me. It's not terms we normally use, and not very descriptive in terms of being able to do any type of technical analysis. Um, However, some circumstances have occurred in the development of my second wing, which made me go back and rethink it. It's always been in the back of my mind. Gee, what happened with the Flare 30? It looks like a great glider. And how could it just all of a sudden fall out of the sky? Aircraft just don't fall out of the sky. But that's exactly what it did. And I'd like to figure out why. Because if we can figure out why it crashed, then we can help disseminate that information so various designers out there don't make the same mistakes again. And without knowing why, well, all you can do is say, "Oh, Flare 30 was bad. Don't do what they did." Uh, but that's not much help. Um, I'm going to take you in for a closer look here. I'm going to take me out of the picture, which I'm sure you'll be glad for, and I'm going to zoom in on this web page from Nest of Dragons and talk briefly about the beginning of the accident, and then I'll come back here and ask you for some assistance in helping me solve this mystery. And if we can solve the mystery, hooray! It'd be better for everybody. So here we are looking at the Nest of Dragons website, and this is the listing for the Flair 30. We see a beautiful photograph of it here flying over some mountains in Europe, and it looks fantastic. Uh, the only thing that bothers me in this photo is that the pilot is in the prone position facing forward, which over time with rigid wings has proven out to be a hazardous position to fly in. Much better to fly feet forward. Doctors tell me that it's much easier to repair legs than broken neck. The aircraft itself looks a lot like my second wing, actually. It's about the same aspect ratio, and it looks similar to the Swift. My first wing was much more Horton-like than this wing. So it's all composite and run to launch and skids to land on. And it's got winglets out here at the end, and it was equipped with elevons and flaps. Let me read to you briefly here if you haven't read through the text already. The Flair 30 first flew in 1990. The pilot could launch by foot and then lay prone in a special harness and finally land on a skid. After extensive flight tests including more than 50 hours, and that's important to note. 50 hours is a lot of flying time. Logged by the test pilot, the prototype was destroyed in a crash at a sailplane club. That's another important point in solving this mystery. We'll talk about that later. When the sailplane pilot flying it dove into the ground at high speed from less than 100 meters. Um, Control reversal was suspected but unproved. By control reversal, it might have meant that the downward pitching effect of sudden flap deployment overrode the pitch up of the elevons rather than the usual kind of control reversal which affects hang glider pilots flying sailplanes or vice versa. And what they mean by that is on hang gliders to slow up we push out, and on sailplanes to slow up we pull back on the stick. And that is really not pertinent here. I don't know why they wrote this. It's not pertinent because the Flair was flown with a side stick controller, so the controls would have been perfectly normal relative to the sailplane pilot that was flying it. Okay, now in the next part here, a guy by the name of Brett wrote in 2005, I received an email from an associate of the Flair 30 test pilot. So this is somebody who knew somebody. And remember that somebody saying some words. And he stated that the test pilot felt the glide ratio and sink rate were quite poor, worse actually than modern flex wings. The test pilot attributed this not to the presence of a hole in the leading edge, as suggested earlier, but rather the pilot positioned over the wing, disrupting the flow at the center, most important section of the wing. Now, those statements are very typical of somebody who's not an aeronautical engineer, who's a pilot, and they believe that they know certain things about aerodynamics, and they do understand certain things, but they understand them in a way that might not be wholly accurate. So this statement here about sink rate and this and the holes in the wings and all that, for the most part, I think we can safely ignore that. Okay, here we are looking at the specifications for the Flair 30, and we have a photo here of the model, I believe it is. So it had 11 square meters of wing area, which is a little on the smallish side, and it has a span of 12 meters. Which is kind of the size that we were working with at that time. It's about the size of my original wing in terms of wingspan, and it's about the same as the Swift. The aspect ratio is 14. That's a little bit higher than the Swift, higher than my first wing, not quite as high as my second wing, which is up around 16 aspect ratio. Of course, there's double surface 100%. That's phraseology that comes out of the hang gliding world because on rigid wings, I don't think I know of a real rigid wing that isn't fully double surfaced. And this was a composite aircraft with composite skins. Kind of a meaningless point there that it's 100% double surface. The nose angle 160 degrees. In the professional aeronautical engineering world, we talk about the sweep at the quarter chord because that's how all of our equations are set up. The nose angle comes out of the hang gliding world. So 160 degrees gives you about 18 degrees at the quarter chord, which is running on the minimum side for a swept flying wing in terms of yaw stability and given the size of those winglets. Flaps go from 0 to 60 degrees. The Swift, I think, does 0 to 45. My flaps go from 0 to 90. Twist, I assume they mean washout by that. There's no minus sign there, but I'll have to assume it's washout. Is 6 degrees, and that also is at the lower end of what you like to do for a nicely damped flying wing. You really want something that's more around 8 degrees. They get a little touchy in pitch at 6 degrees. You can, depending on the airfoil, go one way or the other. It's right on the edge. But that nose sweep angle and the twist indicate to me that somebody was working the design right to the limit of stability in order to try to achieve higher performance. It says here the production model should be under 30 kilograms, which I don't think they would have ever achieved. If you're using composite skins, you just cannot get that light if you got 100% composite skins. I don't know of any way to do it, and I've worked really hard at it. The prototype was in the 50 kilogram area, which is what, 110, 120 pounds, which was spot on. If you're all composite, fully skinned wing, that's the nominal weight that you're going to end up at. And with the current materials, I don't know of any way of beating that number. Not by much, anyway. So the weight they were actually at was realistic, and the 30 kilograms is not. Setup time and the other stuff's not important to us. We get down here, V-min, 30 kilometers per hour, 0.6. So that's down around 18 miles an hour, maybe a little bit more than that, 19, which is about the same as my original wing without flaps. And that's a little bit lower than my current wing at 23 miles an hour. And that's mostly because I've gained a lot of weight. Anyway, so the max speed, 150 kilometers per hour, it's right in range of what you would expect for an aircraft like this. And here we pass out of numbers that are reality into numbers that are kind of fantasy. The max glide ratio of 30 to 1 at 65 kilometers per hour. I think that the speed is correct, but the L over D is not. That is an L over D that you would get out of theoretical calculations. It's spot on for theoretical calculations, but it's not what happens in reality. Flying wings are not that efficient, and yes, you heard me say that correctly. Flying wings are not that efficient. There are losses for a variety of reasons, and you never achieve the theoretical maximum on the L over D. And so I think it'd be realistic to say it had an L over D around 25 to 1. And given the era, that was fantastic. 25 to 1 in that time frame, really super. So here we are. We see that we got numbers that are not too far off of what I'm currently doing or what the Swift did and so forth. They're just kind of pushed to the edge in order to achieve higher performance. So here we see somebody's young son standing there with a model. The model looks to be maybe quarter scale. So at least we know it went through model testing, which will tell you some things and not tell you other things. But we'll have to assume that the model flew fine, because if it didn't, you would move on to a full-scale prototype. And below we have a multi-view, 3-view drawing of the aircraft itself. And let me pause here for a second and scroll down. We'll take a closer look at that. So here we're looking at a 3-view of the aircraft. And from the top view, you can see it looks highly similar to my current wing. Looks very similar to the Swift. They have about the same taper ratios. So the the mean aerodynamic chord is somewhere out in the 40 to 45% of the semi-span range, which is just where you want it for good performance. I've calculated the mean aerodynamic chord, and I'm going to convert units on you here, is about 32 inches, which if you watch my previous videos, you know that that's a critical number. We'll talk about that a little bit later. And I haven't attempted to take any measurements off this drawing yet, but I will in the future to try to get the proportions, at least the proportions correct, but I'm going to approximate them as I speak along here. And we can see it's set up with a little bit of dihedral. I don't know why they did that. Maybe they wanted to get the aerodynamic center or the airfoil up in line with the pilot's CG. Maybe they thought it looked nice. For better stability, you'd probably want 0 to 1 or 2 degrees of anhedral to prevent Dutch rolling. I don't know if they had any Dutch rolling issues with the aircraft. I've never heard anything about that, but they might have. If the winglets are large enough, they would have damped it out. And once I say winglets, I take a look at that and I can see a couple of different indicators here. The top view kind of shows the winglets back, the leading edge of the winglet at the hinge line of the control surfaces, yet the side view shows the leading edge of the winglet at the leading edge of the wing. I don't know which one is absolutely correct, but we'll assume the side view is correct, that they attached the winglets where they had good structure to connect to. And that's not what you really want to do. Winglets on flying wings, you really want that winglet so the leading edge of the winglet is essentially where the spar is. You want it at the leading edge of the winglet at or behind the maximum thickness point of the airfoil. If you protrude the winglet forward into the pressure gradient that's occurring on the leading edge of the wing before you get to the maximum thickness point, you will decrease performance and cause flow problems and so forth. So much better to set the winglets aft of the maximum thickness point. Although most designers are loath to do that because the structure back there is essentially non-existent. So what you have to do in order to get the right aerodynamics, efficient aerodynamics, you have to work a little bit more structure into your wing and eat the weight so that you can mount the winglets where it will create better flow conditions. But it's not something that would have caused this crash. It's more related to performance. So let's take a look at the control surfaces. We see that there's a pair of elevons, and they comprise approximately a third of the semispan. And it looks like they take up maybe 35 or 40% of the chord of the wing. And that's important to note for later. And the flaps take up the rest of the trailing edge. Why did they do that? Probably to make the control linkages simple. You could just put a torque tube in there, put the stick right on the pilot's left side, and he could easily deflect the flaps that way. So 40% of the chord for the flaps is large. I would suspect that the reason they made the flaps so large, took up so much of the chord and so much of the span, is to get a higher CL for launching. We know that the wing area is relatively small at 11 square meters. Nominally, you would not get an 18 or 19 mile an hour stall speed at that wing area with your average pilot. You'd be more up in my range of 23 miles an hour. But with generous flaps like that, you could probably drive the stall speed down lower. And that's probably why they did it. And then they can go down to 60 degrees of deflection for landing, which makes sense. If you want to bring it into small fields, you need a lot of flap to do that. So the only thing that I see here that I would consider unusual is the large area of the flaps. And once I have a chance to sit down and take proportions off this drawing and see if I can find the root chord and tip chord and the mean aerodynamic chord and where the aerodynamic center is, we'll be able to find out whether or not when you deflect the flaps, whether the nose pitches up or down. Could be either way. Depends on the position of the aerodynamic center of the flaps relative to the aerodynamic center of the entire wing. You look at some other numbers here. Some of these numbers are not consistent with the numbers that we had up above, but we'll assume close enough. And here's the important thing, and why all of you are hopefully still listening to this video. I need your help. I need to find the coordinates for this airfoil, the CM-140K47. I've looked all over and cannot find those coordinates. I don't even know whose airfoil this is. From the drawing, it looks like it might be a Wortmann airfoil, but I've looked at all my listings of Wortmann airfoils, and there's no numbering like this at all with those. And in order for me to figure out or confirm or not confirm my suspicions about why this crash occurred, I need those airfoil coordinates. I need to run through some software here and look at the flow conditions on top of that airfoil. And if it's what I think it is, then we would have an answer and we'd know exactly what happened. But without those airfoil coordinates, I cannot say for sure. So ask your friends, ask around, keep asking, ask, and find me those airfoil coordinates, and you'll help everybody out. I'll be able to do the analysis, and we'll know one way or another whether what I think is correct. And if I am correct, then we can solve this mystery and pass the information out to the general public so the same design errors don't occur in the future, hopefully. You can send them to my email, which I put in the description down below, or you can just hit me up in the comments and say, oh, here's a link. You can go find those coordinates at this link. Anyway, most likely to be somebody in Europe that knows that series of airfoils. Hopefully it's not something that the designer designed and he's the only one in possession of the coordinates. They'd be very hard to come by then. So dig through all your materials, see if you have it hiding somewhere. And then I will go do the full analysis and we'll find out, maybe find out what really went wrong. What I think it is I think it's the same phenomena that I've run into on my current wing, where past a certain angle deflection of the control surfaces, you get instantaneous flow separation. All the flow just turns 90 degrees and runs out to the wingtip due to the uh, sudden drop in pressure on the upper surface of the wing due to deflection of the control surface, and that drop in pressure occurs about 1 inch aft of the hinge line, and all the flow after that just turns 90 degrees and goes out to the wingtip and stalls the wing. And if the pilot was coming in for a landing and overshooting and he dumped flaps really fast, that could have happened, and then it could have literally separated the flow almost over the entire wing. And in that case, yeah, the nose would drop and you'd fall out of the sky. So it has nothing to do with control reversal, but would have a lot to do with flow separation because of the low Reynolds number that we're flying at and the small chord here. That you know, if you watch my previous videos, that 32 inches is about minimum that you want for these speeds that we fly at, and that's the mean aerodynamic chord on this thing. It's 32 inches. So the tip is smaller than that, so that could be problematic. Part of the flap has less chord than that. The root section may be okay, maybe not okay. It depends on the airfoil. If these airfoils, if this was a low-speed airfoil uh, designed for low Reynolds number, then maybe not a problem. Don't know, but I got to have the coordinates before I can figure that out. Uh, but either way, if it's what I think it is, there is no way the designer would ever know. No way that anybody would know, because I believe it's a phenomena that's previously unexplored. That pressure spike is well known to aerodynamicists, but its effect at low Reynolds number and what happens with the flow on the wing is essentially unknown up until my recent work. And now we know what causes it. We know how to prevent it. We don't cut control surfaces out of the wing. We put flat plate control surfaces on the trailing edge, and then that avoids that problem. Uh, and I'd like to sort this mystery out. And that's where you can come in and help find those coordinates for me, please. And uh, uh, and and I'll be back with part two and do the analysis as soon as somebody sends me the coordinates. And until then, as I always say, fly safe and bye for now.